I'd like to thank our speaker, Dr. Sumit Mukherjee, for having time in his busy schedule to present the topic here. Dr. Sumit Mukherjee is a senior machine learning scientist in INISTRO, and he'll be talking about practical tools for privacy preserving synthetic data generation. So, Dr. Sumit, over to you.
Thank you so much for the invitation to the organizers. So today I'm going to talk about some of the work I've done at the Alphabet Research Lab at Microsoft on developing practical tools for privacy preserving synthetic data sharing. The main motivation behind this line of work is, data sharing across institutions is obviously very useful for scientific discovery. However, in certain fields like healthcare, there are very stringent legal restrictions to share data across institutions. And there are, a lot of existing regulations around this, such as GDPR, but, a lot more similar laws are coming up in, variety of countries. So with this in background, we were interested in the question of, whether we were interested in seeing if we could develop new tools, algorithmic ways to kind of, help share data across institutions while overcoming legal hurdles. So one solution that was that caught our eye was synthetic data. So basically, there's been a lot of great work in generative machine learning in recent years, which has led to a lot of models that can generate realistic synthetic data after training on real data sets. And the synthetic data can then be used downstream for a variety of tasks. And a naive assumption that a lot of people make about synthetic data is that, since the samples are synthetic, you're not leaking information about individual samples or people. But this is not true, and I'll explain how later on in the talk. So since, I'm mostly going to be talking about generative machine learning models, let's introduce a very simple generative machine learning model called GAN. So GAN stands for Generative Adversarial Networks. It's a machine learning model that comprises of two modules, the generator and a discriminator. The generator attempts to generate realistic looking synthetic data, whereas the discriminator tries to, tell real from fake. So it predicts the probability that an image is real or fake, right? And these two modules are trained iteratively. So eventually the generator learns to generate, samples that are almost like the real samples. So in mathematical terms, it learns to kind of like approximate the data distribution. And so, one has to ask the question, can, a model like this leak private information? And the answer to that is an overwhelming yes. And to see that, we look at this very simple experiment. So as I mentioned before, the discriminator outputs the probability of a sample being a real or a fake sample. So what we did was we took a GAN, trained on some training data set, and through its discriminator, we passed all of the samples that were used to train it, right? And plotted the distribution of scores in red. You can see here. And we also had a held out set of samples, which are real samples, just not used in training. And we passed these through the discriminator and plotted the distribution in blue. Right. So what you can immediately see is these two are very different distributions, right? And if there's an adversary who can, utilize, if the adversary's goal is to predict like whether a sample was from the training set or the held out set, if the distributions are so different, then it can do, it can predict the set membership quite effectively, right? So the less similar the distributions are, the easier it is for an adversary to identify, individuals, the set membership of individuals. So at the time when we started working in this area, there were, some existing solutions, namely the differential private generative adversarial networks. I'm not going to go into a lot of detail about differential privacy, but it's a way to bound the privacy of algorithms. It leads to very strong formal guarantees, and generally involves addition of noise during the model training process in one form or another. However, there's a huge problem with these models, which is that it leads to really poor synthetic image quality, even though it protects against a very wide range of attacks, right? So question that we, asked was, this is obviously not going to work as a practical solution for data sharing. So can we come up with a more focused subset of attacks while sacrificing less utility? Right. So that obviously brings us to the next question, what attacks should we focus on? So my team was mostly interested around in healthcare data sharing. So we spoke to a lot of clinicians, and there were no clear consensus, and most clinicians didn't seem to understand privacy attacks very much anyways. They did know that they had to meet the legal requirements. So we spoke to some clinicians, security experts at hospitals, and some clinicians with more of a machine learning background. And so after speaking to them, the general consensus was that an approach that would prevent re-identification would probably pass legal hurdles. So working backwards from there, we identified membership inference attacks as a class of attacks that, if we mitigate them, will probably meet the requirements of the clinicians. Right. So what are membership inference attacks? Membership inference attacks are a class of attacks where the adversary has access to some number of samples, and all they want to know is whether the samples were used to train a machine learning model or not, right? They have some query access to the model in question, and so they can take their samples, query the model with that sample, get some kind of output, and then use an attack model to predict the membership. Um, and for such attacks to work, the query values should obviously be different between the training and the holdout samples. And this happens when models overfit to the training set, as we saw in the toy example for the GANs. So to kind of develop a solution to this problem, specifically for GANs, we came up with a modified GAN architecture called private GAN or PrivGAN, which is a very simple modification to the GAN. It makes two main changes. So first, instead of training the generator and discriminator on the entire data set, we randomly split the data set into two or more equal parts, and assign a generator discriminator pair to each part. And then the second thing that we do is basically have another machine learning module called the privacy discriminator, which is an internal adversary, whose goal is to look at the synthetic samples generated by each generator and predict which generator generated the synthetic sample, right? So what this achieves, what this extra module achieves, is now that the generator is no longer just trying to generate realistic samples to satisfy its corresponding discriminator. It's trying to generate samples that are not, very particular to its split of the data, right? It tries to generate samples that are kind of somewhat, have the somewhat universal in its properties. And so by doing this, like we're implicitly, it's almost like an implicit regularization, and we show that mathematically this formulation is equivalent to constraining the distance between the learned distributions of the generators. And we'll show that this prevents the generators and discriminators from overfitting to any data split. Okay, so now that we've explained how PrivGAN works, does it work, right, in preventing privacy? So we redo the same experiment as before. With we now have like the non-private GAN results on the left and the PrivGAN results on the right. As I mentioned before, the closer the red and the blue distributions are, the harder it is for an adversary to tell which distribution a sample came from, right? And in the case of PrivGAN, you can see that they are actually almost identical. However, like with that out of the way, the reason for, going through this line of work was to kind of come up with a method that, even though it protected like a more limited notion of privacy, it led to higher downstream utility. So we want to see like that, it does indeed lead to higher utility. So to do that, we ran this experiment where we took several data sets, trained different GAN architectures. So the gray line is the non-private GAN, then PrivGAN with 3 different privacy settings. So you can weigh the privacy discriminator by different amounts. So the higher the weight, the stronger the blue color. And DPGAN, which is a differentially private generative model with an epsilon of 100, which is like the epsilon is so high that it doesn't actually provide any practical privacy guarantee, but we'll see that even for this ridiculously high epsilon, privacy setting, it still does quite poorly in terms of utility. So for each of these models, we trained it on a training set and then generated the same number of samples as the training set. Used the synthetic samples to train a CNN model, CNN based classifier model, and which was then tested on the real test set. And the 2 baselines we have here are, a CNN model that was trained on the real data and real training data and tested on the real training data, and non-private GAN whose synthetic data was used to train the CNN model and then tested on the real test set, right? And you can see that for all of these data sets, there's barely any drop for PrivGAN for most settings compared to the, I guess, baseline non-private GAN. Whereas DPGAN, even at this high epsilon, has like a very huge privacy drop, right? So again, the takeaway here is that there's very little utility drop for PrivGAN compared to GAN. And if we want to do kind of like more of a privacy utility trade-off comparison, we did that as well. We looked at utility that was kind of quantified using the previous experiment and privacy quantified using a very effective privacy attack from a membership privacy attack described in the cited paper below. So what we did was we for DPGAN we used different settings of epsilon to generate data. And for PrivGAN, we used different weights of the internal adversary to generate the data. So each point is 1 epsilon or 1 value of the weighting for PrivGAN. And you can see that in both these settings, PrivGAN largely outperforms DPGAN. So in summary, PrivGAN was the first non-differentially private GAN architecture to focus on empirically addressing the membership privacy attacks. We showed that it compares very favorably against, DP-based approaches. And in the paper, we show that it protects quite well against state-of-the-art membership inference attacks. However, there was one main limitation of this work, which is there was no formal way to quantify privacy loss, unlike differentiated private approaches. And this is obviously going to limit use because, again, like if you're going to convince regulators that you're providing some amount of privacy, you need some kind of like certificate, right? So the next part of my talk will kind of like address that. So coming to this part of the talk, let's first start by assuming we live in a world where like there are some number of known privacy preserving synthetic data generation approaches, and you're a data and model owner looking to kind of like make some decisions on data sharing, right? So what are some of the decisions you might need to make? You might want to look at, what information should be released to the public. Should you just release synthetic data? Should you release just the generators? We release the full models. How big should your synthetic data set be? How do you choose between different models, which might claim to be membership private? And are there some samples that are more vulnerable than other samples so you can screen them out? And so in this work, we develop a novel theoretical framework to measure membership privacy loss for generative models, which will hopefully answer all of these questions. So to kind of, in order to measure membership privacy, the backbone, we have to set the backbone first, which is kind of done usually using the membership privacy experiment from a classical paper by Young et al. So the way this experiment, conceptual experiment works is like you have the data distribution and you kind of like sample two sets of samples from it, one to be used as a training set and another as a holdout set. And then you train a model on the training set, and the adversary only has query access to the model. And so each time, then you kind of like the adversary flips a coin, picks one set, doesn't know which set it's picking, samples a point from that set, and passes it through the query function. It then sees only the query value and nothing else, and tries to guess which set it came from, right? And if the adversary guesses correctly, it receives a reward or utility of 1. Otherwise, it receives a utility of -1, right? So this is the membership privacy experiment. If the expected value of the utility calculated in this way is called membership advantage. It's a quantity between, obviously it's a quantity between, like -1 and 1. So basically, if you have a membership advantage of 0, it means that you're kind of like doing as bad as random chance. Like, so you have like no, you have perfect membership privacy. If you're kind of like close to 1, it means you have really poor membership privacy. So there have been a lot of recent papers that have used like heuristic suboptimal adversaries to estimate membership advantage given queries. There are various examples of queries that have been used in the literature. In fact, I should say a lot of the work in this line this line of work has been to develop new queries and not so much on like, developing optimal adversaries. So some example queries are discriminator scores, distance of a sample to a synthetic data set, etc. Where some example adversaries are, say, an adversary uses discriminated score as the query and knows that 50 samples off the 100 points, 50 were from one set, all the adversary does is then it sorts the samples by discriminator score from largest to smallest, and then selects the top 50 largest samples and predicts them as training set. And although this might seem like a very simple adversary, it's actually quite effective, as shown in literature. However, there might be stronger adversaries possible for the same queries. And um, additionally, the heuristic adversaries generally only provide an aggregate estimate of privacy risk of models and don't say anything about the risk for individual samples. So we wanted to come up with a more principled approach, which kind of like gives some sort of, I guess, some form of privacy certification that we couldn't get from the heuristic adversaries. And so to come up with a better approach, we first have to kind of understand that the membership privacy experiment is simply binary classification. Right. The adversary, has to make a choice at instance whether a sample given the query value belongs to set S or not. S is the training set, right? In the ideal case, if the adversary knew what the probability Z coming from S given Q of Z was, then it would be able to design the best possible classifier, which is the Bayes optimal classifier, which I'm sure most of you have learned in, like intro to ML classes. Is a very simple classifier, which basically looks at what the probabilities of Z coming from S given Q of Z and Z not coming from S given Q of Z are, and then, selects the highest the higher value as the class. However, this is not a practical classifier since, this quantity, the probability of Z coming from S given Q of Z is usually unknown in classification problems. However, in the setting of, the data owner having access to the model, the training set, some amount of holdout samples, this is a quantity that can be estimated, right? So we come up with sample-based estimators, which can estimate these quantities for both discrete and continuous queries, along with confidence intervals. And we show that these can then be used to derive consistent estimates of membership advantage for the Bayes optimal classifier. And as a bonus, since we estimate probability of Z coming from S given Q of Z, we also have an estimate for the membership privacy risk for sample Z given a particular query. So does this actually outperform heuristic queries? So in this very simple example, we use the heuristic adversary that we previously mentioned that uses discriminator score, knows what percentage of the data was in the training set, and just sorts the samples and predicts the top X% as the training set. That the membership advantage of that adversary is seen in green, and then we try to other, adversaries of our own. So the continuous query is basically the discriminator score directly used as the query for the Bayes optimal adversary. And the discrete query is basically the discriminator score divided into 100 equally spaced bins. So a discretized version of the discriminator score that was used as a query. And in both of these settings, we see that the membership advantage of the optimal adversary is actually higher than the heuristic adversary. We also show a couple of use cases that we previously discussed. So basically, we were interested in the question, how much of the model is safe to release. So to evaluate this, we can, generate two types of queries. One is the discriminator query previously described. The other is the generative query, which is the distance of, of a real sample to the synthetic data set. And we can see that the it's considerably more private to release synthetic data set than the model with the discriminator. I guess it should be it's worth mentioning that the discriminator query is possible only for a full model release, whereas the generated query you can apply to any setting. So in here we use it as a proxy for when only the synthetic data is released. We were also interested in the question, how much synthetic data should we release? So for this experiment, what we did was we took a pre-trained generative model and created several synthetic data sets of different sample sizes, and used the generated query to estimate the membership advantage for each of the synthetic data sets. And the unsurprising takeaway is that the larger the synthetic data set, the more privacy you leak. However, the user could, at any point, also do utility experiments, quantifications, and decide, how much privacy they're willing to sacrifice for their desired amount of utility. Finally, the last use case is, understanding privacy risks of different groups. To understand this, to demonstrate that we could do this, we took a data set of medical images, corrupted 10% of the medical images, and then, use them in the training process, and then calculated the average individual privacy risks for the corrupted groups and the uncorrupted groups. And we find that the corrupted group has a much higher individual privacy risk compared to the uncorrupted group. So in conclusion, MACE, the paper, the name of our framework is a novel theoretical framework to estimate maximal membership privacy risk for pre-trained generative models. It can be used for various tasks, such as comparing risks of different pre-trained models, help make choices about model release, and identify samples or groups in the data with high privacy vulnerability. It can also be used for non-generative models, example classifiers, and yeah, that brings me to the end of my talk, and I'm happy to take any questions.
Okay, do you have any questions in the room, please?
Yes.
I'll take your question.
Actually, my question is that if our downstream task is outlier detection, we should think about which data set. That means image or it is tabular data. That means I would like to ask that which is more challenging to deal with, the tabular data publishing or the image data publishing, if our downstream task is outlier detection.
Right. So image data is generally considerably harder to kind of generate privately. For tabular data, by now, even differentially private approaches have found some amount of success, like particularly if like the tabular data is like not very high dimensional. So approaches like PattyCan can reasonably, generate like, reasonable utility synthetic data, and provides like, good privacy. But for images, there's still like no DP approach that works reasonably well. So you're kind of in the realm of having to use, a bunch of empirical techniques. And so I would say that image data is considerably harder to generate privately.
Thank you.
Thank you very much. How about is there any other question in the room? Our online participant, do you have any question?
Switch on the camera.
Any question from the online participant?
No, I think not.
Okay.
Thank you.
Thank you very much for the wonderful presentation. I'm really glad and hope we'll have you another time. Round of applause for Dr. Sumit, please.